All right, so today we're going to do a few more of those fraction problems, pick up where we left off. We'll do a little bit of scientific notation, and then that's probably going to be what we do for the day. We'll probably get to end a little early since in my main QR classes today, we didn't really cover anything new. We mainly just talked about the project. I mean, that's what we spent, I'd say, 80% of the day working on. Besides that, it was just doing the density problem, which is just another fraction. So there's nothing too crazy with those. That's not the one I wanted. This is the one I wanted. Okay. So again, just kind of picking up where we left off in these fraction problems. If you missed anything from last time, I would suggest that you watch the video from last time where we focused on adding and subtracting fractions for the most part. We dealt with those as mixed numbers. We talked about borrowing. We dealt with them as regular old fractions, proper or improper. We talked about how we had to have an LCD. LCDs came up with mixed numbers as well. What's mainly left is just multiplying and dividing, as we've seen some of. So the fraction 2/3 is said to be the blank of the fraction 3/2. When you pull down your menu, you have the options of reverse and reciprocal. Now, some students might say, oh, well, it's flipped, so it's the reverse of it, but that's going to be wrong. It's actually called the reciprocal. And if you try again, it's just going to give you the same thing because drop-down menu questions are boring. So reciprocal is when you flip a fraction, and we've talked about that. Dividing by a fraction means you multiply by the reciprocal. Reciprocal meaning to flip the fraction. I don't need credit, do I? That's fine. All right, so again, I'm not going to do every single one of the next 20, 25 or so. We're going to just kind of do a couple, since in my opinion, multiplying and dividing is easier. But at the end of the day, the challenge is knowing what technique to use for multiplying, and then the next problem might be in adding and knowing which technique to use for that, and then the next problem might be dividing and knowing which technique to use for that. So you have to practice this stuff enough so that it's not just being able to get it right when you're doing the same thing over and over and over. It's being able to do something right when it pops up randomly, and then randomly another day later, and then randomly another month later, and then randomly 3 years later. All right, so 1/6 times 5/7, just changing my multiplication symbol. There's tons of multiplication symbols. Don't care which ones you use. So if you see any common factors top and bottom, you can reduce or cancel them, which 1 and 6, nope. 5 and 6, nope. 5 and 7, nope. 1 and 7, nope. So in that case, you just multiply straight across. You're just reducing and then multiplying straight across. The 1 times the 5 being 5, the 6 times the 7 is 42, and the answer should be 5/42. 5/42. Checking my work. We got it right. Easy as pie. This one, we got 5/12. Now they put it in parentheses, then 4/7. 4/7. That's what happens when you write and think at different speeds and talk. Now this problem, it looks different because of the parentheses, but it's the same thing. It's the multiplication. This is literally the same thing as this if you want to rewrite it. Now here, you could just multiply straight across if you wanted to. Go away, menu option that you probably don't see. You could just say 5 times 4 is 20 and 12 times 7 is 84. But the problem is that 20/84, if you put this in, it's going to be the wrong answer because, spoilers, it's not reduced. It is much easier to go ahead and reduce before you multiply. So look for any common factors top and bottom. 5 and 12, no. 5 and 7, no. 4 and 7, no. 4 and 12, yes, there are common factors. 4 goes into 4 once and then into 12 3 times. That's weird. So 5 times 1 is 5 over 3 times 7 is 21. Now, if you had done it the other way I mentioned, if you said 5/12 times 4/7, 5 times 4 is 20, 12 times 7 is 84, and then you could go, oh, well, 4 goes into both of these. 4 goes into 20 5 times, and 4 goes into 84. Guess how many times? You're right, it's 21. So you end up with the same answer. It is my opinion that this way, actually, I don't know why I didn't just pull out the highlighter. This way was easier. That's an opinion. Why do I think it's easier? Because I didn't have to do the multiplication and get double-digit numbers, which could have been triple or 4 or 5-digit numbers, potentially speaking. And the reduction was easier because these are smaller numbers. Now, the reduction might not have been too hard to pick out here, but if you're looking at 3, 4, 5-digit numbers, those reductions can be more difficult to pick out. And if there's several reductions or big number reductions, then you might miss something. So it's just easier, in my opinion, to reduce first. And most people would agree with that opinion. 5/21, everything looks good. Everything looks good. Next question. Exponents with fractions. So 2/5 squared, when you have an exponent, like a 2, that just says to take the thing and multiply it by itself that many times. So we take 2/5 times 2/5. A lot of people think it's a lot harder to deal with exponents and fractions. Quite honestly, it's as simple as multiplying because it's quite literally multiplying. So that's just 2 times 2, which is 4, and 5 times 5, which is 25, and that's going to be my answer. And you might say, Mr. Beckner, why didn't you try and reduce first? Because I knew I couldn't. 2 and 5 doesn't reduce, so this 2 and 5 don't reduce, this 2 and 5 won't reduce, and this 2 and 5 won't reduce. It's kind of the nice thing about exponents. The inside of this, if that doesn't reduce, then applying the exponent means nothing else is going to reduce either, because it's literally just the same top thing over and over and over, and the same bottom thing over and over and over. So if a single pair of them doesn't reduce, multiples of them won't reduce. So 4/25, and there we go. All right, how about 9/16 times 3/16? I'm going to do something wrong for a second. This is wrong, 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 wrong. I'm doing this wrong. Oh, 3 and 9. 3 goes into 3 once, and 3 goes into 9 3 times. Oh, 16 goes into 16 once and into 16 once, so that's just 3/1. No, that was terrible. Why is that terrible? Because I was reducing top numbers with top numbers and bottoms with bottoms. You don't reduce that way. So let's do this the right way. You say you can only reduce a top with a bottom, and if it's a product, it doesn't matter which top and which bottom it is. And that's the only scenario you can reduce. You don't reduce when you're looking at two fractions being added or subtracted or divided. You only reduce in this manner with multiplications. And in fact, 9 and 16 can't reduce, so the other 9 and 16 can't reduce, and the 3 and 16 can't reduce, so you're stuck just multiplying straight across and nothing will actually reduce. So 9 times 3 is 21. 16 times 16, 10 of them would be 160. Another 6 would be 96, so that's 256. I'm not going to pull out the calculator just for 16 times 16. So it's 21 divided by 256. Now notice, I don't even think about reducing this. If you can't reduce here, then you can't reduce here. That's one of the really awesome facts about multiplying and reducing. If you can't reduce it first, then you can't reduce after you've multiplied. You don't believe me? 21 over 2, what did I write? What did I do wrong? Oh, 9 times 3 isn't 21. Why did I say 21? It's 27. Simple mistake. 27. Not 2,127, 27. 9 times 3 is 27. I think I probably said 27 and just wrote the 1 accidentally. I don't remember. My bad, though. 5 over 4 times 7 over 6. Nothing's going to reduce on that one. Spoilers. You'll multiply straight across and you'd get 35 over 24. Not going to show that one. Not going to show that one. We'll show this one. 1 over 9 times 12 over 17. 9 and 1 can't reduce. 12 and 17 can't reduce. 1 and 17 can't reduce, but 12 and 9 can. 3 goes into 9 3 times, and 3 goes into 12 4 times. Then you multiply straight across. 1 times 4 is 4. over, that's 17, 34, 51. 3 times 17 is 51, not 57. 4/51, and we get it. Again, remember, you're supposed to be doing all these on your own. Hopefully, the weirdest systems I've ever heard of where we assign homework and aren't supposed to actually assign the homework and grade it. But remember, you're doing these things for yourself. All right, 3/8 times 23/1. Notice that this was times 23. I turned it into 23/1. Now, some people will say, I didn't have to do that and I got the right answer. That's up to you, your skill level, and what you understand. But I think most people probably need to do it this way. Nothing's going to reduce. The 8 times 1 is easier, so I'll do that first. It's 8. Then it's 23, 46, 69. So 69/8. They say to type a whole or simplified fraction. We've already learned that they would probably take a mixed number, but I'm not going to do that conversion because it's just more time, effort, and more mistakes to make. This 2/3 times 9, we should probably write as 9/1. The 3 and the 9 can reduce. 3 goes into 3 once and into 9 3 times. Multiply straight across. 2 times 3 is 6. Over 1 times 1 is 1. Now I'm going to do this wrong. It better mark me wrong. It should mark me wrong. 6/1. Incorrect. Although your answer is the correct answer, it's not in the correct form because anything divided by 1 is itself. So you have to write just that 6 to get that answer right. All right. We mentioned that reciprocal earlier, and that comes up with division. Dividing by a fraction means multiply by the reciprocal. So 2/5, instead of divided by 3/2, I'm going to change that to times, and not 3/2, 2/3. So here's what some people will accidentally do that's a mistake. They'll say, oh, there's a 2 in the top and a 2 in the bottom. They cancel and just make ones here's. Ones here's, ones here and here. You cannot do that. Don't do that. You cannot reduce anything except for products of fractions. So these 2's are in the top, so they don't even reduce. Nothing reduces here. 5 and 2, 5 and 2, 2 and 3. Nope, just multiply straight across, you get 4/15. And that's your answer. You just got to pay attention. You got to process what you're actually doing. That one's another boring one. Boring. Let's see how many more. I think that 35 will be the last one I'll do. Yeah, 35 will be the last one for this stuff. So 21/33. That's a division, so we change it to, what's happening? What did I do? I clicked too many times. There we go. Times the 7/13 is going to become 13/7. All right, well, now we can reduce. 21 and 7, well, 7 goes into both of those. 7 goes into 7 once and into 21 3 times. Now, you might have seen that 3 went into 21 and 33 into that first, and that's okay. But now I definitely see that 3 goes into 3 and 33. So I can take, let me pick just a different color to show you the coordination. 3 goes into 3 once, and 3 goes into 33 11 times. And that's all that's going to simplify before we multiply straight across. 1 times 13. And if you want to rewrite everything, 1/11 times 13/1. Some people like doing that. And you'll get 13/11. There we go. Right, so we're going to skip that one. This is just a random problem in here, just as a reminder of the signed arithmetic. Remember that with multiplying and dividing, 2 wrongs make a right is what some people like to say. It's that 2 negatives make a positive. I can make a positive. So if I have something like 5 times negative 2, that's negative 10 because that's a positive and a negative. There we go. But if I had negative 5 times negative 2, that would be positive 10. Now this works with bigger products. If I have 5 times negative 2 times 3, 5 times the negative 2 is negative 10, then the negative 10 times 3 is negative 30. Some people will just say if they have an even number of negatives, the answer is positive. If they have an odd number of negatives, the answer is negative. But if I did 5 times negative 2 times negative 3, 5 times the negative 2 would make a negative 10. Then the negative 10 times the negative 3 would make a positive 30. So the problem they actually have is 3 times negative 2 times negative 1 times 2 times negative 2. If you want to show these step by step, the 3 times the negative 2 would make a negative 6. And then times the negative 1 times the 2 times the negative 2. The negative 6 times the negative 1 would make a positive 6. And then times the 2 times the negative 2. The 6 times the 2 would make a 12. And there's times the negative 2. And the 12 times the negative 2 would be a negative 24. Let me make sure I got all my signs and everything right. Okay, that looks good. Some people, alternatively, would just say, all right, I've got 1, 2, 3 negatives. That's an odd number of negatives. So the answer is negative, and then just say 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24. Just depends on whether you can do this quicker or if it takes you more time. I don't care as long as you can get the answer. However, you get it. All right. Scientific notation. Just making sure I had plenty of space. This is where you take a number like 4,500, you turn it into what would look like 4.5 times 10 to the third. The left is what we call standard, and the right is what we call that scientific notation. I'm just abbreviating. The goal here, going to scientific notation, hold on, give me a second. Your goal in going to scientific notation is to get the decimal place immediately after first non-zero number. By first, I mean from the left, of course. Count how many times you have to move the decimal. This will be your exponent. Now, a lot of people will say, all right, when you move the decimal, it's positive. When you move the decimal left, it's positive. When you move the decimal right, it's negative. And that's true for going to scientific notation, but it is not true when you're going from scientific notation to standard. It's completely opposite of that. And after people learn both, and they'll do one problem of going to standard, one of going to scientific, and then another of going to standard, and then another going to standard, and another going to scientific, they start getting it jumbled in their head. So I'm not even going to put ink to paper, so to say, metaphorically speaking, what I just said out loud. I'll say it one more time. Going to scientific notation, if you have to move the decimal left, the exponent's positive, right, it's negative. But this is a better way that doesn't flip-flop from version to version. And it is as such. Big numbers, i.e. numbers 10 or larger have positive exponents in scientific notation. Small numbers, which are numbers less than 1, have negative exponents in scientific notation. That's it. That right there, in my opinion, is a million times better than saying, well, when you go to scientific notation, left is positive, right's negative, but when you go to standard, left is negative and right is positive. It's just too much heads and tails to constantly get right. And I'll even admit I'll do it wrong once or twice if I try and do it that way. In my head, this is the way I do things, a better association, a reason to it. Big numbers are numbers that have like 1,000 or 10,000 or 1,000,000, and that's what this 10 to the third represents. 10 to the third represents 1,000, so this is like saying 4.5 times 1,000. 10 to the negative third would actually be 0.001. So positive exponents are big numbers, negative exponents are small numbers. That's the idea. So let's run with that idea, and let's see if we can do this conversion. So when you're going to scientific notation, you're trying to move the decimal immediately. So it was, whoops, that's the highlighter still. That was weird. You're trying to take the decimal, which was behind the last 0, even though you didn't see it, and you're trying to move it between the 4 and the 5. And that would be 3 movements, which is why the exponent's a 3. This was a big number, so it had a positive exponent. When you start in scientific notation, the exponent tells you how many times to move the decimal instead, and it also tells you the direction. Now again, the positive is right and negative is left is true, but I'm just going to think about trying to create a big or small number based on the problem. So let me go back to blue here. There we go. This 1.62, that's all I'm going to write. And then this was times 10 to the negative 7. So that 7 tells me the decimal moves 7 places, either left or right. Maybe I move it right. And I said maybe. In fact, let me use a different color. I might be using red for a reason. It's wrong. 1, 2, 3, 4, 5, 6, 7 times. And there's a bunch of empty spaces. You fill those in with zeros. So that number is really 162 and then 1, 2, 3, 4, 5 zeros. So that number is really 16,200,000, which is a darn big number, which contradicts that negative exponent, says it should have been a small number. So that is how I immediately know that I did this wrong. So what this actually would have been, I cleared my screen, right? Yes. What this actually would have been is 1.62 times 10 to the positive 7. That's what this would have been. It's, you know, it's close. It's still got the 162, but it's positive instead of negative, which says it's a big number. So the way we should have actually done this problem, and I might not have enough space there without making it look ugly. Let me just squeeze it here. Let's take the decimal, blue for correct this time, and let's move it 7 times left. 1, 2, 3, 4, 5, 6, 7. Filler zeros as needed. Some people, most people, especially math teachers, love to have a 0 in front of a decimal place. So that's 0 point, and then there's 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6, and then the 162. That's a small number, which suggests that since it was a negative exponent, I've done it right. So point 1, 2, 3, 4, 5, 6 of those zeros, then the 162, drum roll, and we got it right. Big number, positive exponent, small number, negative exponent. That is going to make your scientific notation conversions 1,000,000 times easier, or 1 times 10 to the 6th easier. Hardy har har. All right, so we're going the other way this time, converting, let's see, that's millions, billions, trillions, 420 trillion to scientific notation. And this is one of the strengths of scientific notation, the ability to take ridiculously big or ridiculously small numbers and just write a lot less. Without these commas, your eyes are going to start crisscrossing if you're anything like me, and it's going to be hard to count them. The commas certainly help. But what if there was, say, 4 or 5 more sets of 3 zeros, and this number is, I don't even know off the top of my head what that is. I also said 4 or 5 because it goes trillions, then quintillions, quartillions, sextillions, septillions, octillions. I always forget the one for 9 sets of zeros. Don't worry about it though. You never have to say that out loud. So we're going to take this number, this 420 trillion, and we're going to take its decimal. It's billion trillion. We're going to take its decimal, which we can't see, so it's right here, and we want to get it right here. That's the goal. To get to that goal, we got to move it left, obviously. 1, 2, 3, 4, 5, 6. Sorry, that got a little ugly there. There we go. 7, 8, 9, 10, 11, 12, 13, 14 times. That's 14 times. So this is going to be, and now I don't need to write these trailing zeros. I don't need all these zeros. That's the point of scientific notation, so that we don't have to write some stuff. If there were zeros between the 4 and the 2, we would have to write them because they wouldn't be trailing. They'd be significant. And then we have our times 10. And then the exponent, since we moved it 14 times, is either positive or negative 14. It's just a matter of, is it going to be positive 14 or is it going to be negative 14? Well, you can do the whole left is this, right is that nonsense, or you can say 420 trillion was definitely a big number, which says this should have a positive exponent. So 4.2 times 10, and then we hit our exponent button, which is right here. I believe it was 14. I hope that's right. Yes. There we go. All right, another one. Express the number point that is 1, 2, 3, 4 zeros, and then 2, 4 in scientific notation. So what we've got is, black please, thank you, 0.1, 2, 3, 4 of them, then the 2 and the 4, and we want to convert this to scientific notation. So this is the same style problem as last time, it's just, this is a different type of number. That was a big, this is a small number. So here's our decimal originally, and its goal is to get between the 2 and the 4, the first non-zero number from the left. So we got to go right this time. 1, 2, 3, 4, 5 times. So that says this will be 2.4. We don't need zeros in front of the 2's in this format. It just looks silly otherwise. So 2.4, then our times 10, and we moved it 1, 2, 3, 4, 5 times. So the exponent is either a positive 5 or it's a negative 5. The question is it positive or is it negative? Well, we ask ourselves, the number in non-scientific notation, is it big or small? Well, that's definitely a small number. Now, again, the big and small idea is not arbitrary. I gave you a definition for that. Big numbers are 10 or bigger. In other words, they have more than one whole digit. Small numbers are anything less than 1, which means there are no wholes. So big numbers are things that have 2 or more whole digits. Small numbers have no holes in the digits. So because that was a small number, this should be a negative exponent. That says it should be 2.4 times 10 to the negative 5. Think about it this way, 10 to the 5th would be a 1 with 5 zeros, which is 100,000. 2.4 times 100,000 would be 240,000, which is not this number. With positive exponents, you should understand how to rationalize what they are. We don't deal with negative exponents too much in this course, so I don't expect you to be able to rationalize them, but you can at least say, all right, well, if this was positive, I see the number would be, what was it, 240,000? Yeah, which is not the original number, so nope, make it negative. All right, so 2.4, then our times, and our 10, and our exponent, and then a negative 5. Hit enter, and we got it right. Next question. Another conversion to scientific notation. And again, I won't do all of these. I don't want to take all the fun. point, this will be fun to count. Let me maybe zoom in just a little bit so I can count easier. My eyes aren't the best. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros between the decimal and the 8. There are 9 zeros between the decimal and the 8. So let's do that. There we go. 9 decimals. I mean, sorry, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the 8, 7. Okay, I didn't count the 0 in front of the decimal. Zeros in front of decimals are just there to be pretty. In case you make your decimal too tiny, you can say, oh, well, there was a 0 there, so maybe that makes it significant. All right, so this is a small number. So I'm going to do this in a different order. Instead of doing the movement, then saying whether it's positive or negative. I'm going to say, since that's a small number, I expect that I should need a negative exponent in the answer. Well, the goal is to get it between the 8 and the 7, so this decimal's got to go right a whole lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So that should be 8.7, no zeros in front, no zeros after. Times are 10. And what did I say, 10 times? Should be 10 times. But not positive 10 for the exponent, small number, so negative exponent. So 8.7 times 10 to the negative 10. 8.7 times, I want to see if the dot will work. It should, but I know there's been at least one math homework program we used in the past where it didn't, so I'm reminding myself. 10, and then to the negative 10. By the way, if you're wondering how I made that exponent without clicking on the mouse, I hit Shift and 6. That's the caret button, which makes an exponent. Again, Shift and 6. And we got it right. I didn't have to do the Shift 6 though. All right, back to converting to standard notation. I designed this to make sure they go back and forth. So we got 2.70 times 10 to the 8th. So I'm just going to write the 2.70 part. Now we're trying to make a regular old number, so no more times 10 with an exponent. So now we got to look at the exponent and say that's a positive exponent. So a positive exponent means we should be making a big number. If that was a negative 8, we'd want to make a small number. Now that tells me which way to move it. If I start moving left, that's 0.2, 0.02, 0.002. These numbers are getting smaller and smaller and smaller. So that would be wrong. That's how you correct yourself. All right, so left is going to make it smaller. Moving it right makes it bigger. 1, 2, 3, 4, 5, 6, 7, 8 times. There's our decimal. Filler zeros as needed in the little spaces. So that number would be 270, and then 1, 2, 3, 4, 5, 6 more of them. 1, 2, 3, 4, 5, 6 commas to make this easier on us. 270 million. And I believe this should take it with or without the commas. I'm going to try with commas, since I know it'll take the regular way. We got it right. Maybe you don't trust what I just said, so let's do a similar question. All right, 8.20, well, that's just going to be the same idea. 820, and then 1, 2, 3, 4, 5, 6 more zeros. And it took it without the commas as well. Unlike a quiz or two that your teacher may have made in Canvas, and he forgot to put the answers with commas and without, just he only did one of them. But we got your grade straight afterwards, didn't we? Those of you in my class. All right, we've done a decent amount that way. Here we go. Convert the number to scientific notation. So we got 730 million. So you might say this number is just 730 and start moving a decimal place. And that would be okay if the word millions was somewhere in the answer, but it's not. So we got to know that this is 730,000,000. That's how much money this is. And we're trying to convert this to scientific notation. So our decimal, which cannot be seen originally, is over here. It's got a goal of getting between the 7 and the 3. So it's got to go left. 1, 2, 3, 4, 5, 6, 7, 8 times. So the answer ends up being just 7.3. We don't need any of those other zeros. We moved it left 8 times, so it's either times 10 to the 8 or it's 10 to the negative 8. It's a matter of whether we need this negative or not. How do we know whether we need the negative? We ask, what was the size of this number? This was a big number, which means that should be a positive exponent. So positive 8. They already have the dollar symbol in there for us, even though I think it shouldn't be. So 7.3 times 10 to the 8th. Drum roll. We got it right. Here we go. The diameter of a certain particle is 0.000009 millimeters. That is a really, really, really small item. In fact, if you wanted to put that in meters, it would be 3 more zeros between the decimal and the 9. So it's currently 1, 2, 3, 4, 5 of those zeros, then the 9. If you had this in meters, it would be 8 of those zeros, then the 9. If you had it in kilometers, it'd be 11 of those zeros and a 9. If you put it in nanometers, it would be only 2 of those zeros and a 9. So that's the strength of having different types of units, because you can make the number appear bigger or smaller, just make it look less ridiculous. Scientific notation also has that strength of you can get rid of just a lot of empty space that you don't maybe necessarily need to see, that can be demonstrated in a more compact form, especially if you're dealing with something like 10 to the 26th or 10 to the 50th or 10 to the negative 26th or negative 50th. All right, so we got our 1, 2, 3, 4, 5 of those zeros and then a 9. So there's our particle. And we want to write this in scientific notation. So the decimal needs to go immediately after the first non-zero number, which is the 9. So its goal is right here, but it starts here. So it's going right. 1, 2, 3, 4, 5, 6 times. And this in scientific notation is just going to have the 9. You don't need to write 9.0 because 9.0 is the same thing as 9. So 9 times 10 to the, we moved it right 1, 2, 3, 4, 5, 6 times. So it's either positive or negative 6, one or the other. Was 0.000009 big or small? I hope you know it's a small number, which means this should be a negative exponent. So it's 9 times 10 to the negative 6th. Nine times 10 to the negative 6. And we got it right. All right, these last three are pretty much the same thing as everything we've already done. So I don't want to just keep doing the same thing over and over and over. Again, I highly encourage you to complete all of these, especially with things that you need refreshment on. If you're good at your fraction stuff, then you don't have to do the problems. If you're terrible with scientific notation, you should probably do these problems. If you're terrible at all of it, do all the problems. If you're awesome at all of it, and you're awesome at everything else in the rest of this course, it just makes me question why you got placed in here, but I know the placement system is not the best, never has been, probably never will be. There's always challenges with that, but I'm not here to rant about placement. So what we'll do is we'll do a couple density problems and we'll call it a day. So we'll take maybe another 10 minutes. As a reminder, density is the ratio of either mass to volume, or when we're being a little more lenient, weight to volume. Again, weight and mass are not technically the same thing, but in a quantitative reasoning sense, they're interchangeable. Because most people think of kilograms as a weight. Oh, well, if you live in England, you might say, I weigh 100 kilograms. That's technically a false statement. You don't weigh 100 kilograms. Your mass is 100 kilograms. Your weight might be 100 pounds, but your mass would be 100 kilograms. And again, that 100 pounds is not 100 kilograms. Please don't think that's what I'm trying to say. It's about 1 kilogram is about 2.2 pounds roughly. So density is the ratio or rate of mass to volume. So density is mass over volume, or again, in this class only, we can really consider it as weight to volume. So I might say you have a package that has a mass of 150 kilograms, and the package is a rectangular box with dimensions as follows. The length is, let's go with 30 inches. The width is 15 inches. The height is going to be 7 inches. What is the density of your package? So you got some box being shipped to you maybe, and whatever materials you just ordered, sounds like a lot of dog food maybe. I don't know, I don't think you could fit that much 150 kilograms of dog food in that box. You definitely need a bigger box. So you got some weights in there. I don't know, computer parts, something. It's in a box that's 30 by 15 by 7 and all in inches. And that box weighs 150 kilograms. So we just want to know, what's the density of this box, the density of this package? What is the ratio of its mass to its volume? I did not tell you the volume, so the first thing you have to do is you have to know that the volume of a box is length times width times height. So that's 30 inches times 15 inches times 7 inches. And no, the order does not matter that you write those in. So we're going to do 30 times 15 times 7. And that'll give us that slightly large number, 3,150. And then that's inches, 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 all being multiplied. So it's inches cubed, not just regular old inches, it's cubic inches. So now all we have to do is take the mass, which was the 150 kilograms. Again, some people would call that a weight. And again, in the real world, no one's going to care that you call it a weight, but technically it's a mass. And we're going to divide 3,150, but we got to make sure we do it in the right order. Is it mass over volume, or is it volume over mass? You actually have to memorize that. And it's the mass is in the top, the volume is in the bottom. So it's a weight per cubic whatever, or mass per cubic whatever. So the density, the mass, was what we were given, which is the 150 kilograms, divided by the volume, which was the 3,150 cubic inches. So let's see what we get when we do this. 150 divided by 3,150. And you get 0.047619, blah, blah, blah. Let's take that to 3 decimal places just for a little more accuracy, which would be 0.047, but the 6 tells us to round up, so the 7 becomes an 8. So 0.048. Remember, your homework always tells you how to round. I'm just doing this on the fly. So that's 0.048 kilograms per cubic inch. You could write it that way, or you can write the word per in there. This is a nice answer, but that number is really small, and some people just don't like really small numbers, and they say, all right, well, 2 of your dimensions were more than a foot. This one's like a half a foot. So maybe I'm curious of what the density is based off of cubic feet instead of cubic inches. You can certainly do that. You could have changed all of these 30 inches to feet by multiplying by 1/12, the 15 multiplied by 1/12, the 7 multiplied by 1/12, along with the units to get rid of the inches, out with the old, and get in feet in with the new, and you'd end up with cubic feet. And you'd end up with a much smaller number. But you can also just take your answer, this density, let's convert this to kilograms per cubic foot. So you have to remember that 1 foot is 12 inches. That's the conversion factor that I'm going to multiply by, but doing it once won't be enough. So I'm going to take that 0.048 kilograms in the top and then cubic inches in the bottom. I'm going to multiply by, we're trying to get rid of the inches and go to feet. So 12 inches over 1 foot or 1 foot over 12 inches. Well, the inches are in the bottom originally. We want to get rid of them. So in our multiplier, the inches need to go in the top. So inches in the top, feet in the bottom, and it's 12 inches is 1 foot. But this is only a single inch that would only take this 3 down to a 2. There's still 2 of them left, which is why I have to do that again and then again. So that's why we multiply by the conversion factor a second time. So now there would only be 1 of these left down here. And then we do it again so that all 3 of these inches will cancel all 3 of those inches. Now there's feet, feet, feet in the bottom, which makes the bottom units feet cubed. The kilograms is still on the top. We didn't get rid of that. And we just got to know what is that 0.048 times 12 times 12 times 12. In fact, I'm not even going to use the 0.048. I'm going to use the number before I rounded it. So I'm going to take the exact answer my calculator has here and just multiply it by 12, and then by 12 again, and by 12 again. And rounding to, let's just do this at 2 decimal places, it would be 82.29. So 82.29 kilograms per cubic foot. It just depends on how you want the answer to look. It depends on, if you're buying something and trying to fill out a certain space, certain density, whatever, it depends on what the units are on the thing you're buying and what you want your units in. So maybe the problem is in cubic inches, but for some reason, it's better for you to have things in cubic feet just because it's more commonly used. It depends on the context of the problem. It depends on what you're dealt. Now, I said in this problem, I didn't use the 0.048 to multiply. I actually used the exact number in the calculator. Let me show you what we would have gotten if we did this with the 0.048. 0.048 times 12 times 12 times 12. And we get 82.94. So 82.94 kilograms per cubic foot if you used the 0.048. So 82.3 versus 82.9, they're only off by 0.6. That's not the end of the world, but that is because we rounded the 0.048 and then used it to process something else. I've mentioned several times that when you take a rounded number and then try and find something else, it usually causes that answer to be worse. And then if you take that rounded answer and then process it for something else, that's going to be even worse. So that's why we like to use non-rounded numbers as often as we can and only round actual answers. And if that answer needs to be used later, maybe go back and use the non-rounded version of it so you don't have these error propagations. That means error just progressing through the problem and getting worse and worse and worse, generally speaking. Now again, this last bit was not, the converting was not part of the original problem. I didn't ask for that in the original problem. I just did it so that we could bring back the dimensional analysis full circle here. Again, you might say, what's this point? Why am I going to do this? Well, let's go back to another topic. We talked about surface area and flooring and stuff like that. So maybe when you go to remodel your bathroom, as your teacher points at himself, you measure your dimensions in inches. So you get out your measuring tape and you measure, it's like, oh, 60 inches by 42 inches, whatever. And then you go and figure out your total square inches, your total area that you have to cover in tile. And then you go to the store and you say, oh, wow, these things aren't actually measured in square inches, they're measured in square feet. So then you got to take the number that you came up with and then convert it. So you got to multiply it by 12 inches over feet, 12 inches over feet, or whatever. Or actually, the other way around. I'm just talking the problem through. And then you would get a drastically different answer. So like my thing in square inches might have been in the thousands, but then when I convert it to square feet, it's probably going to be like, I don't know, 10 or 15. So it might be like 1,000 square inches, and then that's only like I said, in the ballpark of 10 or 15 square feet. So it sounds like a bigger number is square inches, but in this instance, the reason the units would need to be converted is because you measured in inches. When you go to the store, the tile is measured in feet. Again, technically feet squared because it's talking about surface area. Now, if someone knows that in advance, they can certainly just do the measurement in feet and then multiply and boom, they're done. But if you don't know that in advance, or you go to another store and their things are just done differently, you got to know your conversions, or hope that someone in the store knows how to do math. And I'm never going to promise that someone in the store knows how to do math.
All right, so that is where we're going to call it a day. Like I said, get out a little early since we didn't get too much done in regular class today. Plus, I figured that would be nice, and spring break is immediately on the horizon for y'all. So hopefully y'all can get some good work done, stay on top of your MDE assignments as well as the Math 154 assignments. Take a look at that project, start working on keeping track of all your budget stuff, all your expenses for this month, look into trying to prorate some of your more major expenses that might only happen once a year or twice a year, things like that. But besides that, have a good break. As always, email me if you have any questions, and we will see you back in on Monday. What is that? The 14th, the 15th? I don't actually have my calendar in front of me. The 14th. Yes. All right. Take care.